Thank you, Shreya, and a very warm welcome to everyone. My name is Shridhar Prabhuraman. As introduced me, I've been associated with MRC for almost over a decade now, and I have done my master's in artificial intelligence. Um, so both the maritime domain and artificial intelligence is something that I have had some experience of. Um, so today I will be going through a lot of content per se, 2 hours of presentation. So let's hope that you guys are able to sit through it. Um, what we'll be covering today will range various topics. While I was listening to a few of comments and few of questions that have been raised, I tried to add a bit more content to make it more relatable from that factor. Uh, So before me, Catherine has already spoken about what marine spatial planning is from a policy perspective and tried to speak about what advantages MSP brings. What we'll be talking about is how technology drives UDA, and that is where we plug in marine spatial planning and why we need innovation in the existing tech stack that we have for MSP. Followed by that, we'll basically get a brief understanding of under the hood what is artificial intelligence. As I understand, we have a diverse diaspora, and that is so the aim here is to get so next time when someone says we are using AI for doing X, Y, and Z, you'll be able to get an understanding of at least an overview of what they actually mean, whether they mean a supervised learning technique, unsupervised learning technique, what kind of algorithms are present, and that will help you bridge the gap of understanding how AI actually plays a role in trying to reduce the requirement of data availability for most of the applications that we have today. Followed by that, we'll focus a bit on the applications of UDA MSP, real world applications, and how AI is accelerating the insights through the MSP that we have. Um, Lastly, we'll have a small case study of the Godavari Delta erosion, more from the perspective of sediment management per se. So before we begin, we all understand underwater domain. We all understand what underwater domain awareness is. Idea is that we want to try and collect and gather as much information as possible, as much data as possible in the underwater domain to be able to assist us in various applications, be it real-time monitoring of events and other such kind of predictive analysis or risk assessment, whatever that might be. We want to gather data, we want to understand what's happening underwater, and then drive our solutions focused on that. While it is not 100% solution towards a problem, it does help mitigate the challenges to a great extent. Um, but we definitely need to recognize some of the disadvantages that we have. The underwater domain is a data deficient and poorly monitored domain. A, this is not a problem of a single country, but a global problem because it is extremely difficult to be underwater and collect any kind of information. We spoke about side scan sonar, sub-bottom profiler, and other such kind of equipments. Every equipment has their limitations. Um, the role of AI, that's where the role of AI comes in. With partial data, how can you construct a complete picture? With incomplete data, how can you construct a complete picture? That's where artificial intelligence per se comes in. Um, right. So the first problem, underwater domain is data deficient and poorly monitored. So any kind of conventional monitoring mechanisms, they are ineffective. Optical, radio, satellite-based technologies, all of them have limited penetration underwater. So it's very difficult to identify what's actually happening there. Uh, the economic feasibility of actually having a persistent sensor network throughout domain is technically challenging as well as economically not viable. What SOSUS has done is not something that is extremely effective to be done throughout the IOR rim per se. Um, and on top of all of it, even if we do have all that information that we try to gather, the marine conditions keep on changing dynamically. The weather changes, the sea state changes, everything keeps on changing dynamically. So any kind of data that we collect is fragmented and it is intermittent. And therefore, what we need is basically a platform or a particular solution which I mean, this is kind of a conceptually bringing towards policy and technology together, which is what I believe the speakers before me have also stressed upon. We need policies in place that make sure that all the data is gathered and collected in a single platform, which is where marine spatial planning actually comes into picture. It is not just about modeling. It is not just about putting everything into a single place. It's not just about seeing the data in a platform. It's more from the perspective of multiple agencies being able to share data together, having APIs that different agencies can use. If agency one has collected a data, they put it on a platform, then agency two can just extract the data from there and use that. That's what we are aiming and that's what we are building that. And this goes far beyond agency, as I explained for this goes far beyond the agency. It will also go towards the local communities, how they can assist, how they can contribute towards the data collection, and how that can help in return to for us to enable providing better solutions. So coastal communities definitely depend on fisheries, aquaculture, and ecotourism. More than 3 billion people globally rely on seafood as a primary protein source. And we know that shipping noise is one of the the largest amount of noise that we have in the ocean. That disrupts marine habitats, that reduces fish stocks. Seaweed and shrimp farming, the aquaculture we have seen has grown rapidly. So climate change is causing a lot of ocean acidification, coral bleaching, and rising sea temperatures. Even if we do say coral bleaching is happening, how do we identify? I mean, again, as I said, it is not possible for us to go underwater, identify what are the different regions where coral reefs are present. Then we need a mechanism, a simulation engine, a mechanism that allows us to predict where the coral reefs are present, what amount of damage could have happened to the coral reefs, depending upon different factors, depending upon temperature, as with the chlorophyll content and other such kind of factors that are there. Uh, so that's where we bring all of this together. And maritime security risk definitely is one of the other component that we look at. Illegal fishing, smuggling, unauthorized vessel movements. If a vessel turns off their AIS data, it is extremely difficult to then. Rising maritime threats. Existing problems including illegal fishing, smuggling, or any kind of unauthorized vessel movements where a vessel turns off their AIS data, and then if any kind of movement is happening, how do we identify such kind of vessels? Again, as we move forward, I will show some of the work that we have done in those respective domains of vessel path identification, basically using the historical data, using historical pattern of ship movement to identify what are the different locations where a ship can be if their AIS transponder is off, and so on and so forth. Um, so now, while we have spoken about all the different challenges and how we have identified that there is definitely lack of data, what allows us to bridge that gap is also marine spatial planning. So while the speakers before me have correctly spoken about marine spatial planning as a governance tool, marine spatial, like what we foresee MSP as, is more than that. It is about how different how different agencies can come together to share data, and then how we can extract information from it and perform some operation. Now, the concept of MSP is not new to us. It is not something that we have established now. MSP has been there for quite some time now. Back when the Great Barrier Reef in 1980s was established, they identified that a lot of degradation is happening. And the degradation is happening because anyone is allowed to use any form of the habitat that ends up destroying the habitat. So what the government back then did, they established the Marine Spatial Planning, or Marine Park Authority is the organization which established the Marine Spatial Planning Act, and they identified that there is a certain zone of the coral Great Barrier Reef that can be used for general fishing or tourism. There is a certain zone which can be used for habitat protection zones where only limited human activities can take place. So like a diver can go and dive and identify things, and there's a no take zone. So like there is no human activity involved. So a third zone where it is completely just preserved and nothing is happening. But even to identify what zone needs to be a general use zone or a habitat protected zone or a no take zone, we need information. We need information to be not just one static information, but we need it to be continuously be gathered across multiple platforms. So, which is where they basically use all this information about the data coming from the sea state, the temperature, to identify how much of the coral reefs will get damaged over time, and all those kind of things. So they simulate across a period of time, and then they identify based upon the multiple factors They demarcate the zones and say that in these zones, these kind of activities are permitted. For India, the MSP, it definitely supports economic growth. It supports our ecosystem health and as well as the maritime security. And it all aligns to the Sagar vision that we have. Um, but that was what MSP was earlier when it started. Today, MSP in India is something that we are performing in collaboration with Norway as part of the Indo-Norway Integrated Ocean Initiative. However, if you look at the map, while there are certain countries which have MSP has been approved and implemented, there are certain countries, with India being one of them, where MSP is still under progress. We have either, like as per this chart, we have not officially started MSP, but we have not been received a revised chart where we have now initiated the process of developing our own marine spatial planning. Why it matters for India is that as compared to other countries, we are looking at a much more larger exclusive economic. We are looking at much more larger ocean surrounding our subcontinent, and that means we have approximately 2 million square kilometers of exclusive economic zone of opportunity and responsibility in area. And we like Indian Ocean today is one of the most important sea areas globally. We are the focal point of maritime trade. We are a focal point in geopolitical hotspot and everything. Everyone has eyes on the Indian Ocean. So we need to have our hold on what the waters that we have. We need to have our hold on what's happening under our own waters and identify and understand the information there. So any kind of MSP, and this is what I was talking about. MSP is not just so decision support system, a system where you can see all the different kind of information, all kind of data that is present globally, is not just a static content that we present. Existing systems, DigitalOcean platform, the WIO Symphony by Nairobi Convention, Australian Marine Spatial Information System that's present in Australia. All these systems that you see are static. It's not just India. It's a global phenomenon that all the existing marine spatial planning systems are static in nature. What that means is that someone collects data. The data is being collected between, let's say, 1980s to 2010. All that information is being collected, and that is what is basically portrayed onto the planning tool. However, what we need is something a bit more than that, because we have one big problem of having a fragmented and we being extremely reactive. A latest report from 2020 by World Bank has reported that the traditional marine spatial planning and coastal management in India has often been fragmented and reactive, and that multiple agencies operate in silos with unshared data sets. So there's a lot of uncoordinated decisions that happen because of that. So many states have even struggled to formulate an integrated marine plan due to the limited amount of data or data sharing and technical capacity. So lack of data is not just about lack of data collection, but rather more about lack of data sharing that we have. And data sharing is not just about agencies collecting data, but also inputs that we get from coastal communities and otherwise. So let's take two examples for that matter to just bolster upon what I mentioned, that there is a lack of data sharing. In Tamil Nadu, there was coastal erosion that was happening. There were hard structures, sea walls and grounds that were built to prevent local erosion. But what they did not take into account is the modeling of the sediment flow, how the sediment flows. What ended up happening is that this only shifted the problem downshore to a different region. It did not really fix the problem holistically. This is not my statement. This is a statement written by the paper where it says that the siloed fix ignored the sediment dynamics, failing to consider how sediment flows and wave patterns change seasonally or with climate-induced variability. So what ended up happening is there was a worsened erosion. Another example where there has been a stakeholder conflict is that one of the biggest organizations in the country, they created a mega port. However, that construction of mega port completely removed the habitat in that region. That means that coastal communities that are present in that region are no longer being able to support their livelihood because of that habitat. Again, the Reuters interview mentions that the protest leaders, so the construction of the port they mentioned has a significant erosion on the coast and building promises to wreak havoc on the livelihood. So this resulted in a lot of protest and a lot of problems to existing community, which is why what we suggest and what we are building on NMRC is a modeling and simulation based MSP, which is not just about static data, but essentially using the static data, you want to identify a different multiple what if scenarios. So for example, uh, what happens to fisheries and tourism if a certain area is designated for mining? How coastal habitat will fare in 10, 20, or 50 years with different climate trajectories, and so on and so forth. So this gives us two specific advantages over the existing static MSP. One is dynamism, which means that the tool that we build is something that will continuously adapt to the changing marine condition and as per the stakeholder needs. And the second thing is the impact modeling, as I talk about how if you, for example, if you perform dredging in a certain area, how that is going to affect the ecosystem. If there is an increase in the marine traffic, or if there is a port development, or any other such kind of activity, how all of that action will affect the ecosystem. So before we build a port, we need to perform an environmental impact assessment. So an MSP tool, a simulation-driven MSP tool, is something that will simulate and identify what kind of impact will happen, environmental impact will take place after the construction of port is happening. The case for modeling and simulation, therefore, is that we need to have a layered approach. We the first layer needs to be historical data streams. By in a lot of situations, we do not have the possibility to continuously monitor the underwater domain. What we rely on is the historical data stream to identify the pattern of how things are and how things flow. This essentially includes AIS and vessel traffic data, human activities information that we have. Again, this comes from the community engagement, uh, depending upon which location you are in, the infrastructure, biodiversity, habitat data, and everything. Then we run that through a simulation engine. That simulation engine will essentially either be a hydrodynamic model, or it can be an agent-based model, climate projections, ecosystem model. There are a whole lot of models that can be integrated into the platform. Uh, we will see one example of the Brahmaputra area of flood management as we move forward, something that we have done in MRC. Then the impact analysis, like once we have the simulation done, then it comes about the habitat risk forecasting and basically analyzing the impact of what's happening because of what we have simulated. Again, none of these outcomes are 100% accurate. They are not meant to replace the existing data. They are not meant to be trusted 100%. It is supposed to be something that supports the decision that comes after that. And that's where so instead of targeting the resources in a wider area, the resource targeting happens in a smaller subset of the region, because we know that the probability of the incident happening in a certain location is more, or the probability of any kind of operation is more in a certain location. Again, I know I'm being a bit generic here when I say certain incident or operation, but I hope I can explain further as I show some examples of work that we have done. And with this, once you have something like this, then comes the stakeholder consultation part, which is then can be used for an adaptive MSP plan, which is what allows us to drive the policy narrative forward. Um, Now, the first question that everyone might have is that, sure, okay, we can have a marine spatial planning in the real world in India. How do we really see what kind of benefits do we really have? So to present that case, there are three case studies that I present. One is the shipping noise modeling part. Of course, I talk a lot about shipping noise and URN because I've been working in that area for an elongated period of time. But the applications are widespread. Now, off the coast of Sri Lanka, scientists have modeled. So what happened was that uh, due to an extreme amount of shipping and extreme amount of noise in the region, they found that there are a lot of whales that were the unique blue whale population was continuously declining. Uh, what they identified is that just by shifting the shipping lane by a few nautical miles, they were able to drastically reduce the decline in the blue whale population. Now, this happened because they were able to map what kind of shipping traffic is there in the region, how the shipping lanes are, what is the existing habitat, what is the migration pattern of the existing uh, marine habitat, and so on. So when all of that information comes together on a single platform, you can then identify that, okay, then you identify that if I move the shipping lane by so much, then the MSP tool is something that will simulate that if you move the shipping lane by so much, this is the amount of reduction in the noise of shipping that you can possibly gain. And using that information, then you perform the operation. So that's one case. Then habitat impact forecasting. Majority of the coral reefs we have been shown to be destroyed by 2030. Damaged and degraded by 2030. And this is a world scale report, which means that India definitely does fall under it, and we need to make sure that our ecosystem is surviving throughout uh, the different climatic conditions. To be able to address the problem, we need to first identify what the problem is. We need to first be able to identify where that problem actually occurs. And that initial stage is where MSP helps in. Um, Now, a strong case why a traditional MSP, where like you collect the data and put it in a particular location, and then just extract that information. Why that static MSP is not suitable for India? For India, simulation-based MSP is more of a strategic necessity because first we have extreme variability. Our coastline faces very high variability in climate, biodiversity, a lot of human activity. I mean, if you look at the amount of shipping traffic that we receive, that has increased tenfold in the last decade or so, which is a huge amount of increase in the shipping traffic. And of course, with it's a chain effect. Once that increases, there are multiple other factors that come into picture. Uh, so we need to have a tool that can simulate and identify and forecast things rather than so instead of being reactive, we need to be proactive, and that is what modeling and simulation based MSP comes into picture. And when I'm saying modeling and simulation, all of this is dynamic. This is real time. This is not supposed to be that something we do for let's say year one and then we do it again for year two. No, it's supposed to be that whenever you select a particular region, you need to be able to obtain all that kind of information based upon the historical data and whatever we have information so far. Resource constraint, we all know that India cannot afford blanket deployment of expensive monitoring systems. If the same amount of, if let's say shipping, if we take the same case of Sri Lanka and if we say that we need to do it not via modeling and simulation, but rather collect real world data, imagine the amount of expense that would have with respect to just the monitoring system. So simulation based MSP offers a much more cost effective solution to such kind of problems. Data fragmentation, we've already spoken about it. I won't reiterate. The idea being that everyone needs to come together. And the governance complexity is also something that is real. There are overlapping mandates between MOES, MoEF&CC, all the state authorities and everything. So a digital data-driven model will essentially offer you a transparency and interoperability. So which means that interagency collaboration will be much more easier. You'll have a single platform. Whether you need the data or not is not something you might know today. Like on the brink of the situation when you identify that you need some information, the amount of time lost in trying to obtain that information from a certain agency versus just going onto a portal and identifying that okay, this kind of information I have here, the amount of time we save is much larger. um, while all of this is true, it is also important that we are, as a country, we are rich in different languages, we are rich in different governance structures, and this whole whatever we this framework, modeling and simulation based MSP framework that we have identified and are developing on top of is something that's is supposed to be tailored for different Indian context, different local languages, different governance structures, and so on. All right, I'll skip through a bit of these given the timeline. So then what are we really talking about here? I mean, conceptually, we have so far explained what MSP is supposed to be. It needs to be a dynamic platform and so on and so forth. Uh, so in a single statement, if I have to put, the aim is to create a platform that converts raw observations into actionable insights for policy, conservation, and industry. And it is extremely important that we identify the actionable insights. What I'm trying to say is that if I have to give an example, um, traditional MSP, I mean, what MSP systems we have so far will collect the AIS data, it will display that into a system. What we are saying is that don't just display the AIS data, you extract information from it and display that. So you need to be able to see the shipping noise and not just the AIS data in the region. You need to be able to see the acoustic habitat and the migration patterns of the habitat and not just historical data of where that habitat was present in certain past. That simulation, that modeling is what will help and drive decisions to be faster. Uh, Existing MSP touches a whole lot of different domains, starting from blue economy, acoustic habitat mapping, disaster management, maritime safety and security, and so on. And when I say it all needs to come into one conceptual system, this is what we mean. This is the MSP tool that we are developing. As you can see on the left-hand side, you have planning layers, life on land, climate action, industry infrastructure, what are the different marine biodiversity areas, wind noise, rain noise, flood risk assessment. So we are not just talking about what is a C state. C state is something that, let's say, we obtain from NCOIS or other different agencies. NCOIS will upload a data of C state. The MSP tool will actually calculate the noise that is generated from it. Resource mapping, oil and gas, land extension, offshore renewable energy. So in case a leakage, a submersible is leaking somewhere, or just if an oil rig leakage happens somewhere, what are the different uh, resources that we have in the vicinity? What kind of impact will that generate? uh, to be able to predict and to be able to identify all of that in in a lesser amount of time is what MSP as a tool will essentially enable. Um, be it navigability of waterways. So most of our inland waterways, they are not navigable because of the fact that, okay, of course, there's a lot of sedimentation that is happening. Uh, that is one factor, but the other factor is also that because the lanes are so narrow, we don't have any AIS transponders in the region. We have solutions such as virtual AIS transponders and things like that, which basically depends upon it calculates your ship route and identifies collision probability index and so on, then identifies what is the uh, correct route to be taken. But yes, the problem is that we need to have a place where all of this can happen. Dark ship detection is an extremely important aspect. Again, I'll show a lot of, I mean, all of these individually, I'll show an example of as we move further. So the foundation of MSP is that we, as a platform, it needs to integrate a diverse data stream. If you're talking about urban flood mapping as a module, we're seeing we're talking about marine data, which comes from tide gauges, coastal waves, buoys. Then we're talking about terrestrial data, rainfall, elevation, soil moisture. Then remote sensing data that we obtain from images like land use, land cover, and the socio-economic and the human aspect as well is something that is extremely important. Fishing, for example, when we went to the off the coast of Veeraval, we identified that it is not just about when a habitat is rich for fishing. It is not just about, so usually there happens a cycle when due to the when the temperature cools down, the nutrients get replenished in the water, and that's when the fishes come back to a particular region. As a fisherman, you are not aware of that. What you are aware of is something that has been passed down through legacy to identify that these seasons are good for fishing, these seasons are not good for fishing, and the seasons that they identify is much more than just a scientific aspect. It's also rooted in culture and tradition. Some people, I mean, you'll be surprised to also find that some fishing expeditions happen more so on the basis of uh, the duration, more so from the basis of what is the if they have any festival activities going on and things like that. So all of that factors needs to be taken into consideration, and that is where the community engagement part of MSP comes into picture. So yeah, so what we're trying to showcase is that if we take MSP as a tool, and this is what we are trying to build, this essentially has a lot of information that needs to come in, and it needs to map everything right from, if you talk about undersea cable, finding the existing cable routes, finding the bathymetry data, the tectonic stress maps, all of that will essentially help us identify that if there is any kind of uh, earthquake happening, tectonic activity happening, how much, well, like, let's predict which submarine cable route is going to get damaged, right? So all of this essentially helps us be informed about all of that. I think Sir has already spoken about the solution architecture that we broadly engage with, but essentially it's supposed to collect all the information from different varied sources, open source or sometimes non-open source. Like for example, for our MSP tool, we gather data from Marine Traffic and Spire. Those are satellite-based data providers. We gather data from there. We perform a lot of error detection and correction because we identified that a lot of AIS data sometimes is also not accurately transmitted. Then, of course, the spatiotemporal mapping. Uh, Depending upon the location that you are in, the algorithm that is being used are completely different. Indian Ocean region, for example, we are a location where our sound speed variability is high. The temperature is high, which means that the so far depth of the water is high. So based upon those considerations, the algorithm that we use for estimation is different. Sometimes we use a parabolic equation based model, or sometimes we use a normal array model and things like that. Um, yes, so the MSP tool is supposed to, as I was explaining, if you click on the port management, it should show the ports in the region. Just a basic AIS. Uh, what you see here is basically an AIS data. All these small dots is basically ships that are present in the region. Hovering over it does not just show that the ships are present in the location, it shows that, again, with what speed it is moving, but more importantly, what is the noise that is being generated by that individual ship. These are not noise radiated, these are just the noise that is emitted by the ship. So the propeller noise that is generated by the ship, depending upon the speed, whether machinery or propeller. Um, so yes, so what we identify is, so we try to bring that kind of data together and not just about this thing. Second map that you can see here, apart, so firstly we enabled the AI shipping traffic. The second thing we saw is the shipping related noise map that we have enabled, which essentially calculates the how that noise is spread across the different region, how that how transmission loss will propagate. I mean, what kind of transmission loss will happen once the noise leaves the ship, in what locations, and how much the noise will be present in each of the region. All of these things is what we identified. Creating a shipping noise map or any such kind of information system is not innovative in itself if you do it statically, but then to do it dynamically basically means that you need to have a system which can perform these operations in real time. So to give you a glimpse of the amount of computational effort and how AI actually solves the problem, because again, what we are trying to look at is where AI comes into picture in these things. Now, if I have to construct the shipping noise map, we are basically taking the complete grid. Uh, uh, we are creating a quarter gridded manifestation of it. So 0. Right. So we're creating a quarter graded manifestation of it. So like 1/4 quarter of a lat long coordinate is the difference between every two receiver points that we have. Then from each receiver point, we basically take a 200-kilometer radius, because a maximum a ship signal can transmit is for 100 kilometers. So we take a 200-kilometer radius, we identify what are the different ships for each point, what are the different ships that will contribute to that particular uh, single point. And even if I have to say how they, like, even if I easily say that how much they will contribute, that how much they will contribute is also based upon the transmission loss that happens of the sound signal from the source to the receiver. To compute that, again, you need a lot of resources. So if you were to do all of this from without the use of artificial intelligence, you're looking at a linear time scale. So if there is 100 ships and so if there is one receiver and 10 ships, so it's going to, let's say, 10 seconds for it. And if you multiply that, it's going to take exponential growth because the number of ships is increasing. So each ship will have to have that mapping with every single receiver point. So to do all of this is a huge amount of computational effort that is required. And computational effort is required because you are calculating, you're not predicting. Where artificial intelligence comes into picture is that it does not perform calculation, it performs prediction. It identifies the pattern and then it creates a model that can basically just predict looking at the raw data. It is not performing any kind of mathematical calculation on top of it to identify the solution. Uh, so when we use a neural network, so we have you basically created a neural network for the for this area that you can see, where this is completely mapped now. So even if today you go ahead and select a few regions and drag a particular region and select the ships, it will compute the noise level that is present there and portray you. As I was mentioning, the whole computation takes a lot of effort, and how an AI-based model, AI-based system will basically help us truncate that time, the duration. So this is a neural network that we had created, which is supposed to perform the estimation of transmission loss per se. Now, the benefits are twofold here that we're looking at. The first benefit is basically that once you have trained a model, these parameters are not required anymore for you to use that model again. Right. So initially, when you train a model, you need those sound speed values, bathymetry, absorption rate, sea state, and the bottom composition, the seabed composition, other such kind of data is basically required for you to create a transmission loss, a model for a machine learning based model. However, once that is trained for a particular region, so if given that our neural network is basically already trained for this given region, we don't need to keep training it again and again. Uh, Unless there is a significant change in the data, of course. But more or less, some of the parameters that we look at, like bathymetry, temperature, these data do not change much. They are constant throughout a duration. So this allows us for faster computation and also make sure that we don't rely on, I mean, that missing data does not become a concern when these kind of things exist, because you already have a model which can predict the transmission loss. So you don't need to rely on a mathematical model and the data that is required for that mathematical model to function. Now, in the amount of time that we're looking at, if you look at the graph on the right-hand side, now I know it looks like an artificially made graph, but this is actually the result that we obtained. Uh, an existing mathematical model like Pyram, as you can see, it linearly keeps increasing. The time execution time keeps increasing as the number of sender receiver pair increases. So sender is basically the ship and the receiver is basically the receiving unit that we have. Um, However, for a neural network, we can see that there is the amount of time it takes is exponentially less. So if this is log n, then this is we're talking about. So if this is O of n, then we're talking about here at the order of logarithmic level of that particular intensity. And the error rate is not bad. If you the existing models that offer us to compute the transmission loss, if we compare that with what we have created for neural network, the error rate stands out between 0 to 20 decibel between a distance of up to 100 kilometers. After 100 kilometers, the signal dissipates so much that it no longer makes any meaningful contributions towards the overall uh, signal strength. So it doesn't make much of a difference for us to calculate on that. Uh, Once we have the noise map, now if we had just presented the ship and if we had just presented the locations of habitat, that would not give us much of a value. But if a tool is being able to predict the noise, but also being able to, once you overlap the acoustic habitat on top of that, so this is basically an acoustic habitat of sea turtles, green turtles, whales, and dolphins that are present in the region. The ones near the coastlines is what you can see is that of the green turtles. So we can see there is a significant overlap that is happening between the existing marine mammals and the noise that is present per se. And it also gives you a dashboard of this thing. Right. Okay. So I think so far we have basically seen what is, what marine spatial planning really is, and we have spoken about how AI is basically an enabler. So we've spoken about the need for marine spatial planning, or essentially a data-driven solution towards problems when it comes to underwater domain. I mean, that is what marine spatial planning actually is. Um, and we keep saying that AI can do this, AI can do that, and so on. But I wanted to also take you guys on a journey to understand what we really mean when we say artificial intelligence. Like, is it just a black box which does everything on its own? You give an input, you receive an output. Is that all that is to it? Or does it really depend upon, like, you need to choose models, you need to identify what is accurate for what kind of a platform, what is accurate for what kind of a problem we are talking about, and so on and so forth. Uh, and so I have made an effort to try to construct something that I feel AI is best explained when the examples are extremely basic and easily understandable. And then we move towards a bit more trying to apply that to the existing problem that we have in the underwater domain to see how they actually come together. So just trying to get an understanding of the basics of artificial intelligence. So if you look at the official definition, it if official definition of AI basically says that they are nothing but systems that learn from data and intelligently respond to inputs. Uh, the intelligence part is debatable because that intelligence is as much intelligence as much you provide. So it's not really doing anything different from that matter. And we use AI in daily life today, be it any kind of recommendations that you get from your social media or be it your uh, Alexa or anything like that, anything that you basically personal assistants that you listen to music on, your refrigerators and everything. And all of this is continuously collecting data from you. It is continuously identifying what you like, what you do not like, where things fall right now, and so on and so forth. Um, and therefore, all the thing that we basically see, all of this AI that we see in and around us, be it the underwater application, above water application, no matter where it is, all of that can be broadly classified into three patterns. One is an artificial intelligence, a broader term that we call AI, which is basically a technique which enables machines to mimic human behavior. But that's pretty much it. That's a technique. What currently sits under that are two different platforms, two different variants. One is called as a machine learning, which is essentially a subset of that AI technique, which uses statistical models, mathematical models to enable machines to improve with experience. There is nothing fancy happening in the machine learning. These are just basic mathematical models, which mathematics that allows you to predict something. So every single time you're giving it an input, it is just trying to identify the probability of an object being what you want it to be. We'll take some simple examples as we go further. And then the next subset, the deepest layer of that is what we consider to be the deep learning, in which we humans, we ourselves do not know what is happening. That is what is a real black box. If a neural network is, for example, a part of a deep learning model, if it is able to calculate the transmission loss, there is no mathematical calculation that I can identify from that particular model. We don't know what's happening. The reason is because for every single input, it tries to identify its own pattern to formulate the outcome or formulate the result per se. And so broadly, any kind of machine learning algorithms can be categorized into four different formats: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Supervised learning essentially means that you are going to teach the model what it should expect as the data and what it should expect as an outcome. However, we know for a fact that in real world, nothing is like there are so much amount of disparate data set present. Not everything can be supervised. So does that mean that AI cannot be used there? No, it's essentially there are other such kind of models such as unsupervised learning where you do not give AI any kind of teaching. You just give it a data set and say that, okay, this is what you have. Now you need to predict. It automatically identifies the pattern between the different elements and then applies that particular pattern. You're not teaching it what is correct and what is wrong. So while there are many models, depending upon what is the need, what is the application that we're looking at. For example, sediment classification is a supervised learning technique. I mean, it can be supervised or unsupervised. But imagine if you have a set of attributes, you have the attenuation, you have the grain size, you have other such kind of attributes of the sediment. Your model can basically then classify whether what kind of sediment it is, whether it is a clay silt or a sand or what kind of sediment we are looking at. An example of unsupervised learning would be essentially what we spoke about. If you want to essentially perform some kind of clustering, you're not going to teach the model anything. It will automatically try to identify that, okay, four parameters are common between these attributes, so they belong to one group, and the other parameters are belonging to some other group, and so on. Let's try to take a very simple example to begin with. Uh, Imagine you basically create a small model. What you want to essentially create is a model that can predict what kind of a fruit it is. Whether it's a tomato, it's a banana or a brinjal. Again, these are vegetables. Okay, so whether it's a tomato or a banana or a brinjal, and only thing that you're able to give is the shape and the color of it. So you're teaching the algorithm to say that anything that is round and red is basically a tomato, anything that is curved and yellow is a banana, and anything that's oval and violet is a brinjal. Okay. However, in real world, the problems increase. There might be an apple that is present there, which is also round and red. So then now the model increases what was earlier an efficiency of 100% because it was able to really see the difference between or really see the features that contribute to a particular object have now changed. So now there are two objects which have the similar kind of features. Both tomato and apple have a similar feature. What that means is that now the model is going to give a 50% accuracy because it's going to say that you have two attributes which are the same, two objects which have the same attributes. Um, and so the model's accuracy goes down critically. Um, so what we then do is we try to extract the information from that particular existing set of data that we have to make it as much more learnable for the model as possible, which is what data science is all about. Which is what, so whenever we say that someone is performing any kind of data science operation or whatever, uh, what they're actually doing is they are taking a particular set of data, they are trying to extract information from the data to make sure that the model can learn as effectively as possible. They are not changing the code of the model, they are changing the data that we supply to the model. So instead of saying red, yellow, violet, and so on, we actually give it a bit more parametric value. So we are saying RGB. So every color is basically consists of a band of red, green, and blue. So you give you give numerical values to it. So the red, green, and blue values of a tomato is going to be very different from the red, green, and blue band values of an apple. And that is how now the model can easily differentiate between the two objects and the accuracy increases. So the idea of teaching the model, so all of this is actually given to the model. You are teaching the model to say that so there is a training set that you provide to the model and say that this is what it is and this is what the fruit is going to be. And then it is able to predict it. Uh, if you were to apply the same thing again, as I explained, for the sediment type classification, same stuff. If you have acoustic attenuation, grain size, the depth, the water temperature, and the sediment type, you're going to teach the model to say that these three, all these properties belong to this type of sediment. Next time, when the model is going to come across any kind of data set which has an acoustic attenuation of 85, grain size of 0.2 meters, a depth of 20 meters, and a water temperature of 19.5 no, 19.5 degrees Celsius, uh, because it has already been trained, it's going to look at the features and it is going to perform a prediction to say that this is a sediment type of sand. So that is what classification is all about. It tries to classify a given object into one of the available bands that you have taught it to be. If we do not give the model enough data, it will not be able to perform prediction. So as such, it is not a magic where it tries to perform all kind of correlations on itself. You are the one who provided that kind of information. And this, I mean, while from an underwater domain perspective or a maritime domain perspective, there are multiple applications. I will also look. I read an interesting article where, uh, and I also captured that in one of the slides forward, where in the US, the military has been seen to use the data from its own vessels to identify the maintenance window of that particular uh, uh, maintenance window of their equipment. So you use that data to try to identify what is the maintenance window for that particular system, and that model will give you, because that data is there. You don't have to perform that kind of operation and so on. Um, so while one end of supervised learning, wherein we teach the model, is classification, the other end is regression, a simple uh, mathematical regression that we apply. A model uses the same kind of techniques. Uh, so for example, if the prediction, so any kind of classification always happens on non-continuous or discrete set of data sets. So it can either be apple or it can be orange. It cannot be a value between apple and orange. But then what if you're talking about things like salary or temperature or any kind of numerical values, where the values can be anything. My temperature can my water temperature can be anything starting from 20, I mean, starting in the bottom of the oceans, if it's, let's say, uh, 6 degrees or 5 degrees, it can vary from 5 degrees to 27 degrees, and it can be like 5.2397 something, anything, any random value can be there. So then what we use there is more of a regression and not classification, because you need to then find the curve that best fits that particular uh, numerical data that you have. So if, for example, in a given example, if you want to identify, you have a given set of values to say that a person who is having a salary experience of 2 years earns a salary of 40,000 and so on and so forth, then what would be the salary that you should be providing for a person who is having an experience of 9.5 years? Of course, there are multiple factors that comes to it, but imagine if this is all the values that you need to consider. In that particular case, what is model doing internally is basically just plotting those data points in a particular line map, and is trying to draw a line that best fits all the, and best fits in the sense the the distance between the line that it draws and all the data points needs to be minimal. So that's what regression is all about. So it will basically try and draw the line across multiple ranges and see that which part is best fitting. So that's a simple curve fitting that we essentially perform. Uh, that's what any kind of linear regression essentially is. And these models, linear regression, classification, there are multiple types of regression, linear regression, logarithmic regression, and so on and so forth. But classification, regression, these kind of models are not resource intensive, because you are teaching them what to do. There is an algorithm that is running behind them. There is no magic that is happening in those particular model. If you want to use it from a maritime perspective, again, if we say the noise estimation of the noise of the ship, if you have the speed with which the ship is moving, the power of the engine, the distance the ship is yet to cover, the total depth of the water, or the hull where the ship is submerged, and so on, what kind of noise level you basically get. This is nothing but, again, a factor of regression, where you have all the different values and it tries to identify what kind of noise value is predicted from that particular ship. Now, the applications, again, as I said, are varied. The examples that I gave are very minimalistic, very simple examples, but the logic remains the same no matter what application you go for. Uh, I just came across this when we were having discussions of underwater search and rescue. So we found an article where an unmanned, so in the area of Scotland, where there are a lot of oil rigs and offshore wind farms, the amount of accidents that have been happening is increasing. So what they are doing is they are training unmanned lifeboat which can automatically venture and identify and rescue people from the vessels. So what this basically, so there is no model which is accurate in the very beginning. Just like humans, the models need to be trained for years and years before they come into an operational status where you can rely on it completely. However, to begin is the more important aspect. Uh, to be able to invest in such kind of technology and expect returns immediately is not possible. That model needs to be trained as well. It needs to understand what the real world conditions are, what kind of water temperatures we are looking at, what kind of wave height is there in the region, and so on and so forth. It tries to learn from all those kind of things, and that's what most of the companies are doing. Again, this is the one that I was talking about, the US Army, which turns to predictive maintenance to cut the mishaps because it is extremely important for them to make sure that their vessels, or in this particular case, their aviation helicopters or anything that is required. The main small problems which would otherwise create a massive havoc can be solved using uh, machine learning very easily. So it can anticipate the maintenance needs. How many more years are there before part X needs to be serviced? So that reduces the mishaps and accidents and so on and so forth. And there is a model, I mean, it will perform the work for us. Now, what we saw right now is a supervised learning where we basically tell the model what is right, what is wrong, what should an apple look like, what should an orange look like, what should a banana look like. What if you do not have that information? Because in real world, you very less often do you have that kind of information where you are able to teach the model what is correct and what is wrong. In that case, what we have is an unsupervised learning where you do not give them any kind of labeling. We do not provide them any kind of data set. So applications, if you look at it, for example, if you want a satellite that continuously studies the images and identifies unusual patterns, you give it, let's say, thousands of images, it's going to keep learning from those images. It's going to keep learning the patterns from those images. The moment there is a new construction that is happening, there's a military activity or there is any kind of vessels that are going off track, which is what we have used for vessel identification. Once that historical data, when that piles up, when there is a new activity that is happening, it will start alerting and saying that there is a new activity that is present, and what I have identified is not something that has been there historically in the uh, data set that I have. Uh, it is not humanly possible for us to pre-label any kind of real-time data set per se. It is not possible that we try to establish a pattern between them. So we just provide it to such kind of models, and these models automatically learn and pre-label, and they are the ones who do that heavy lifting for us. Um, yeah, so if we take the same example, but in a different concept, if let's say you do not have that information of what each item looks like when you pass it through an algorithm, it's going to group them. It's going to say that, and this is what clustering is all about. So clustering is a form of unsupervised learning where you give it the data, it will try to group those data based upon the different attributes that it finds to be accurate. And then based upon that, it will provide an output. So it will see that all a subset of fruits look together. So it will group all of them together. And it will see that there is only one fruit which is not part of any groups. So that is basically considered to be an outlier. That is how it essentially captures an outlier. Same example, if we perform the sediment type identification using clustering, wherein, for example, you are not able to teach the model, you are not able to tell the model what what a sandy silt is supposed to look like, what is a clay is supposed to look like, and so on and so forth. It'll automatically perform that clustering for you because it's trying to see is that all the data points that are looking similar, will group them together, and then they need to, if the elements that constitute the object are same, then the object that it is trying to predict is the same one. So that's the logic that it tries to apply for that. Right. So broadly, these are the different aspects. These are different. When we say machine learning is basically used in basic sense, this is what is actually happening in the backend for any of those things. Of course, these machine learning models are nothing but a complex mathematical functions that have been created, computed, but under the hood, the logical or the framework that they follow is what we have seen so far. Now coming back to the part of marine spatial planning and the use of AI to basically drive underwater domain awareness. Let's have a look at the different elements, the different domains where underwater domain awareness and AI in general, and it basically shines. Uh, so basically, we've done some work on inland waterways, creating aids to navigation for inland waterways, sediment classification we have performed in tropical waters for sediment bearing pressure and so on, satellite-based sediment bed load estimation. So we currently, the biggest problem that we have is that sediment bed load prediction is a huge challenge. We cannot, I mean, even if we use side scan sonar or other such kind of sonars, to what extent will we be able to perform that kind of an operation? How much will we be able to map it? Do we have, I mean, the resource constraints? I mean, the resource constraints is one part of it. As we spoke about earlier, even if you have collected the data, there is no way for you to transfer that data easily to anyone or anywhere. What you need is, again, different ways in which you can identify the sediment bed load. Again, it depends upon the application as well. I mean, if I were to say that the example that we saw of a neural network, that transmission loss being a 20 decibel error rate, 20 decibel error rate when it comes to shipping is not much depending upon the application that you're looking at. If there are two vessels that are, let's say, 120 decibel and 140 decibel together, the overall noise is just 140 decibel. It's not going to add both of them. They're going to be logarithmic, right? So when the addition itself is logarithmic, the 20 decibel error rate is just plus minus 5% in that sense, and it is not going to impact the application. So depending upon the use case, the resources that are required for it is also, if I'm supposed to, let's say if I'm performing port construction in an area, if I want to perform environmental impact assessment, does it offer me any benefit to have hydrophones that are located, like, that are deployed in multiple regions, trying to identify what kind of sound is there, noise is there in the region, if I'm really just looking at the shipping noise aspect of it? In that case, then marine spatial planning, I mean, the MSP toolkit or such kind of use of AI and modeling and simulation is much better as compared to deploying hydrophones. And the idea is to mention that this can be done. We don't need to have such kind of equipments to perform these operations. Uh, so yes, so basically understanding the sediment dynamics, understanding sediment transportation is a big challenge that we have today. We all, I think, sir already spoke about how much I mean, how much we need to, we have siltation levels in the rivers and uh, water bodies and so on. To be able to identify what kind of sediment it is, using satellite image is one of the works that we have been taking up. There is a, I'm sorry. Yeah. So there is Romit is one of the researchers who will perform, who will explain more on that as we move further. The other part is the shipping noise and vibration studies. Again, we have spoken enough about it. There is a lot of applications for it: global shipping impacts, marine fauna protection, and so on and so forth. Acoustic habitat mapping, again, as I had shown you the map, where we basically predict what are the based upon the chlorophyll content, because we don't look at where we found blue whales. We don't look at where we have spotted blue whales or dolphins. What we look at is what is the food for those blue whales, what kind of environment is required for those blue whales, dolphins, and sea turtles to be present in. So that is the data that we provide: the chlorophyll content, the content on the turbidity of the water, the temperature of the water, and so on and so forth. And these information are present in terms of the data set, both open source as well as closed source. So using that, you can then identify the acoustic habitat for these marine mammals and so on. Snapping shrimp mapping. Uh, one of the researchers again will talk about, I believe, tomorrow. Uh, the area productivity and yield analysis. We will be surprised to know that most of the most of the uh, people who cultivate snapping shrimps, they have this idea to, they assume that the more amount of shrimps that you cultivate in a pond, the higher the growth of the shrimp is going to be, the higher the productivity is going to be. However, they completely miss out on the fact that the more the shrimps are present in a pond, the nutrient concentration that is going to be there is going to be reduced. Uh, Even though they feel the stocking density is going to increase at the end of the cultivation period, what it ends up is decreasing, because that nutrient is not getting equitably distributed between the shrimps in a healthy manner. So we basically developed a tool which, given certain parameters, it will try to predict you what kind of water temperature is required, what kind of salinity is required, and it will predict you what is the overall stocking density that you should be expecting at the end of cultivation period, and so on. Uh, flood mapping, again, something we spoke about earlier. Simple hydrodynamic modeling, when added to MSP, when you use historical data along with it, you're able to identify what are the potentially flooded areas. Like if for a given Brahmaputra region, we were able to identify what are the areas which are potentially flooded, which are the areas which among those areas are affected by cropland, which among those areas are urban areas, and so on and so forth. So having this kind of information ready, I'm not talking about just the data, having the complete simulation ready in your hands is what marine spatial planning is all about. And this provides much more information than just knowing what kind of rainfall is there in a particular region. This is much more impactful than that. Dark ship detection using SAR analysis. You capture the data from satellite images. We basically try to identify what kind of ships are there in the region. This is more from dark ship detection, more from the perspective of AIS transponders being off for ships. We try to see what is the probability of each of those element to be a ship, and what is the speed with which that ship is moving. That is also something we can easily predict with the amount of data sets we have. And all of this is open source data set. There is a dearth of data because the satellite rotates. You will not be able to capture the information at every instant, but that is where the historical data comes into picture, because then you establish a pattern and you fill in that gap using historical data, and you let the machine learning model derive from the historical data that what bridge that gap and try to identify the ships. Yeah, I think I'm going a bit over time as I identified, so I'll try to cut short a bit. So yes, so sediment is the physical currency of any kind of coast. Any kind of upstream work that happens is like, although we talk about maritime domain, underwater domain, everything has a link. I think, as sir mentioned in the very beginning, the importance of the fact that we are majorly covered by water. Everything that we do upstream also has an impact on the downstream. If you have the forested slopes, those forested slopes are going to reduce the soil loss. If the area is deforested, there is a massive amount of sediment wash that is going to happen that will end up causing turbidity. That basically means that at the coastline, there's too much amount of sediment and the corals and seagrasses suffocate. However, at the same time, if you have dams and other such kind of things, there's a too little amount of sediment and the beaches erode. There are two prime examples. Maybe I have only explained the Godavari Delta erosion, but Kerala 2018 floods is also a good aspect to look at. So in the Godavari Dam, what essentially happened was that even though it was the most important part of the peninsula, when people saw that there has been a dramatic decline in the overall sediment load that is present over the past 5 to 10 years or so, 5 to 10 decades or so. And that study essentially showcased that because of the fact that the sediment delivery dropped, what used to reach to the coastline has been now deposited behind the dams. And so when the dam is basically now exposed or open, the complete sediment is now uh, uh, drenched down towards the shorelines. Mangrove forest, which is an extremely important part, they need a appropriate balance of freshwater and sediment to, to basically progress. But when you do not have that, they become stressed, and the amount of salinity in the region increases. So what we essentially need is an integrated action which relies on both the ecosystem, safer communities, and sustainable blue economy. And that is where we bring in the fact that MSP will provide us the structure and the long-term planning for the marine side. And UDA is the one that provides the real-time underwater intelligence to validate the land and the sea linkages to understand what's happening underwater and use of marine spatial planning. With that, I wrap up my presentation. Thank you.